Today it's our pleasure to host Professor Ruth Daly. Ruth received her PhD in astronomy and physics at Boston University, and she currently serves as a professor of physics at Pennsylvania State University in the Berks campus. And her research interests include black hole physics, extragalactic physics, and cosmology. So please, Ruth, take it away.
Thank you. Thanks a lot. All right, I'm going to share my screen and open the PowerPoint. I have a couple of screens here, so let's see. All right, can everyone see that all right?
Yes.
Great. So I'm going to be speaking about black hole spin and accretion disk properties that are obtained with a new method to study spin and disk properties. And it's going to be applied to 750 plus sources, a little over 750 sources, and it's summarized in these 4 papers. So, as many of you know, black holes are characterized by their mass and spin, astrophysical black holes. And there are very few methods to obtain and study black hole spin. So there's strong motivation to try to develop new methods to obtain and study black hole spin and accretion disk properties. So that's what I'm going to be focused on today. And as I mentioned, the results I'll be presenting are summarized in these 4 papers. As a bit of background, it's been known for a long time and thought for a long time that powerful collimated outflows from black holes are probably powered by black hole spin. And this goes back to the 70s and 80s. For example, the Blanford's and Yaik paper, I think it was 79, the Reese paper in 84, Bagelman, Blanford, and Reese in 84. I have a paper in 2011, Narayan and McClintock in 2012, and many, many other people where there's not enough room to list them all. So here, I'm going to be using the properties of the outflows to study the spin properties of supermassive black holes and stellar mass black holes. As a byproduct of these studies, you can also determine the accretion disk magnetic field strengths, the mass accretion rates, and the radiant efficiency factors of the accretion disk. And this is all done without specifying a particular accretion disk model. So in some sense, it's model independent. And at the end, you can use these results to study accretion disk models. Now, when I use the term accretion disk, I'm using that to refer to the matter in the vicinity of the black hole. It doesn't have to be in a highly flattened structure. So I'm using it very loosely just to apply to whatever the mass, the matter around the black hole. In the end, the results highlight the role of the accretion disk as a source that maintains the magnetic field that is anchored in the disk and threads the black hole, extracting the spin energy of the black hole and powering the outflow. So here are 3 pictures. One is an actual radio image of Cygnus A. And if you're not familiar with these sources, these are called FR2 or classical double radio sources, and they're very large compared to the size of the galaxy. So the elliptical galaxy would sit inside the radio emitting region. The black hole is located coincident with the radio source in the center. And these are very, very large extended classical double radio sources. So I'll be discussing one sample of FR2 sources. I'll be discussing 2 samples of AGN that are associated with compact radio emission, where the radio emission is coming from a region quite close to the black hole. And then I'll be discussing a sample of stellar mass black holes that are parts of X-ray binaries. So in these systems, the black holes have masses of around 10 solar masses. They're located within our galaxy. They have a companion star, which provides mass through mass transfer and produces an active source that allows these to be observed and studied. The key parameters to study these that have to be empirically determined are what's known as the beam power. The beam power is the energy per unit time put out in the form of the highly collimated outflow. It's generally thought to be in the form of directed kinetic energy by the time it is impacting the ambient medium and leading to a radio source, either a powerful extended FR2 radio source or a compact radio source associated with an AGN or a stellar mass X-ray binary. The beam power is the most difficult parameter to determine empirically. I've used two different methods to determine the beam powers empirically for the results that I'll be showing you today. The total radiant luminosity of the accretion disks, so that's all of the electromagnetic energy released in the form of light from the accretion disk, is referred to as the bolometric luminosity of the disk. And there are several well-established methods to determine the bolometric luminosity of the disk. So that is an empirically determined quantity that's fairly straightforward to obtain, and the methods to obtain that are well accepted and widely used. The third key parameter describing these systems is the black hole mass, which in what I'll be showing you is given the symbol capital M, or it's equivalent to the Eddington luminosity of the source. And there are also several well-accepted and well-studied methods to determine the black hole mass. So I won't spend a lot of time explaining how the bolometric luminosities and black hole masses are obtained, but I will spend a little time explaining the empirical methods to determine the beam power. And these three quantities, these three empirically determined quantities, can be combined and studied to solve for the black hole spin and the properties of the accretion disk. So the outline of these key developments and their use for the outflow method is described here. The new method that I've developed to determine spin and accretion disk properties, I refer to as the outflow method because it's based on the properties of the highly collimated outflow. All right, so I'll mention the way that the outflow beam powers are determined. And that includes a new interpretation of the fundamental plane of black hole activity. And that will lead to 4 samples of sources for which we will have beam powers plus bolometric luminosities and Eddington luminosities. Now, after we obtain these beam powers and the other quantities, we're going to look at a new representation of the key equation that describes a spin-powered outflow. These will be combined, the empirical results and the new representation that describes a spin-powered outflow, to solve for the black hole spin and the accretion disk magnetic field strength. Okay, I will show you after we do that, that the spins and magnetic field strength obtained with this new method for half dozen or so sources overlap with values obtained independently. And in those cases for which a comparison is possible, the agreement is quite good. Next, independent of points 1, 2, and 3, we can go on and write down the beam power as a function of the mass accretion rate in physical units and use the results to solve for dm/dt, the mass accretion rate, in both physical and dimensionless units. That can be combined with the bolometric accretion disk luminosity to solve for the radiant efficiency factor of the accretion disk. And again, all of this is done without specifying a particular detailed model for the accretion disk. All right, so as I mentioned, the key parameters are going to be the beam power of the outflow, which I denote L sub J, a standard way to represent the beam power, the energy per unit time dumped into the radio emitting region. the bolometric luminosity of the accretion disk. So this is the ratio of the beam power to the bolometric luminosity of the disk. And here I have the bolometric luminosity of the disk in Eddington units. So everything on this diagram is empirically determined. So there are no model inputs here in terms of a particular accretion disk model or a detailed model for jet production. So how are those quantities determined? Well, for the FR2 sources, the beam power is obtained using a method called the strong shock method, which I developed over the course of the 90s and have worked on with many collaborators. Our most recent paper on this is O'Day et al. In 2009. And the idea is you apply the equations of strong shock physics to the large extended radio emitting region. And when you do that, you can solve for the beam power. One of the nice features of this method is when you do that, it has almost no assumptions. A key assumption that often enters analyses of this type is whether or not the relativistic radio emitting plasma in the large extended radio emitting region is in what's known as minimum energy or equipartition conditions. The nice thing about this method is this is independent of that assumption. When the deviations from these conditions are input, they all cancel out. So they enter into several terms, they all cancel out. So the result is that the beam powers are very reliable. In addition, the beam powers obtained with this method are the basis of the use of FR2 sources for cosmological studies, for example, to determine the coordinate distance, or since redshifts are known for all the sources, that's the same as the luminosity or angular size distance. All those cosmological results obtained are very similar to those obtained with type 1a supernova, and they have been studied for both the radio galaxies and type 1a supernova out to redshifts of about 2. The agreement is remarkably good and applies not only to the cosmological parameters, but in fact, it agrees in detail with coordinate distances and first and second derivatives of the coordinate distance with respect to redshift out to these redshifts. And my most recent paper on that goes back to 2008 with George Sturgovsky, a longtime collaborator on those cosmological studies, and a few others. This means that these beam powers are reliable. I'll skip the methods of obtaining the bolometric luminosity and the black hole mass, but for the FR2 sources that have all three quantities, there are 97 sources in the sample I'll be showing you. And then there were 3 added later. So some results have 97, some have 100. So in addition, I have developed a new method of using the fundamental plane of black hole activity to obtain the beam power. And that is illustrated here. And I applied that to 3 samples of compact radio sources. So the fundamental plane for black hole activity is a relationship between the compact radio luminosity of the source. So now we're talking about compact radio sources, such as Seyfert galaxies and liners, another type of AGN, and stellar mass black hole systems. So this has been found to apply over a very, very broad range of mass, about 9 orders of magnitude, relating the radioluminosity of the compact radio source, the X-ray luminosity of the gas around the source, which we're calling the accretion disk, and the black hole mass. It extends over 9 orders of magnitude in mass, indicating that it's mass scale invariant. So the simplest similar equation that can be written down in mass scale invariant form is equation 2, which in fact has a functional form just like the one I found in 2016 for the FR2 sources. So we're now going from 3 parameters to 2 parameters. So it's the beam power in Eddington units and the bolometric disk luminosity in Eddington units, and relating them as basically a line in log space. Now, relating the bolometric luminosity of the disk to the X-ray luminosity, the 2 to 10 keV X-ray luminosity, which is in this equation, they're just related by a constant, and the Eddington luminosity is, of course, a constant times the mass, and a power law relationship between the radioluminosity of the compact radio source and the beam power. It's very easy to show, as I did in my 2018 paper with 2 undergraduate students, that this allows you to solve for the beam power where the constant C is determined empirically using the coefficients from the fundamental plane. The coefficients little a and little b here determine this value of C. And the constant D is a combination of constants from all the other factors here, plus some of the fundamental plane values, little a and little b, and this quantity, capital B, where for what I'm going to show you, I use the value I obtained for the FR2 sources in my 2016 paper. The key point is that mapping the fundamental plane to the fundamental line, that is mapping equation 1 to equation 2, provides an empirical determination of the beam power without having to write down a detailed model relating the luminosity of the compact radio source to the beam power. All right, so these are the results obtained with that method, those methods, all right? So this is the ratio of the beam power to the bolometric luminosity. We see it spans 4 orders of magnitude for these 4 samples versus the luminosity of the disk in Eddington units, which spans 6 orders of magnitude. Interestingly, the slopes of these all turn out to be quite similar. And of course, the slope obtained for the FR2 sources is completely and totally independent from the slopes obtained for the fundamental plane sources. So we notice they're all quite similar. So the fundamental plane sources that I'm going to be talking about include 576 liners presented by Nisbet and Best in 2016, and those are shown in green in all of the figures. The 80 AGN from the original Merloni et al. Sample in 2003, where the fundamental plane, including AGN, was discussed and introduced, which included the black hole mass. And those are all shown in red. Prior to this, the fundamental plane had been discussed for stellar mass black hole systems, but it did not include the black hole mass because for those systems, the black hole masses are all quite similar. And then there are 102 measurements of 4 galactic black hole systems. So these are the X-ray binaries, the 10 solar mass black holes that are parts of X-ray binaries. And those sources are highly variable, so it's important to have simultaneous radio and X-ray measurements. Of course, the black hole mass remains fixed, but the radio and X-ray luminosities are changing. And so there are 102 independent measurements of the 4 galactic black hole systems. All right, so you might be familiar with the term a disk-dominated AGN system or black hole system and a jet-dominated black hole system. And jet-dominated systems have beam powers greater than the bolometric luminosity of the disk, okay? So I'm seeing a question here. Do these have error bars? Yes, they do. And I will be showing you those in a little bit. They, when you put those on this diagram, it's too messy to actually see anything. All right, so, but I will be showing the uncertainties in a little bit. They're around 0.2 or 0.3 or so in the log, the uncertainty of the log. So they're small compared to, you know, these tick marks over here. All right, So these are the jet-dominated sources, and these are the disk-dominated sources down here with bolometric luminosities greater than the beam power. And we see that there's no difference at all in any feature of this on this figure. So the slope is the same, does not change with bolometric luminosity in Eddington units, and the normalization is also the same. So there's no indication that there's any change in the physics, the underlying physics behind these sources. And this suggests that they're all governed by the same physical process. Now, these sources up here with beam powers that are, 10 to 100 times larger than the bolometric luminosity of the disk are almost certainly spin-powered outflows. It's very difficult to come up with mechanisms to produce something with a beam power 10 to 100 times the radiant luminosity of the disk. And since they all of the sources on this plot are on lines with very, very similar slopes and normalizations, that suggests that these are all spin-powered outflows, okay? And keep in mind, everything on this diagram is strictly empirically determined. Now, throughout the talk, I'll be referring to this quantity A, and the slope of the line shown here are A minus 1. So A is a slope of Lj over Led versus Lbol over Led. I'll be showing you that in a little bit. So this would have an A of about 0.44, 0.43, 0.41, 0.47, okay? So we'll be seeing this quantity A throughout. It's empirically determined for each sample separately, as explained here. And here it is. So here's the beam power in Eddington units versus the bolometric luminosity in Eddington units. And here's the slope A that we'll be referring to later on. Now, you might notice that there is a very, very sharp cutoff when the bolometric luminosity of the disk equals the Eddington luminosity. That is a result. That is not externally imposed. So when I go to take a normalization factor for the beam Lbol over Led, I will take that to be 1. So the constant of proportionality describing the maximum possible bolometric luminosity of the disk. However, for the beam power in Eddington units, this cuts off at about 0.1. So the normalization for the beam power written in Eddington units will be 0.1. Now, that's all empirically determined. Now let's look at the theory. Let's assume that the outflow is powered at least in part by the black hole spin, as indicated by the very, very large beam powers shown earlier. Now, there are so many papers, I could hardly list them all, so I only mention a few here regarding the beam power. A spin-powered outflow, of course, Blanford and Zinayak in 1977 wrote down this equation. Meyer in 1999 showed that if you have a combination of a spin-powered outflow plus a disk wind, as in the Blanford-Payne model, you recover the same equation. And this has been studied in numerical simulations by many, many groups. So the beam power goes as the poloidal component of the magnetic field strength squared, and that's the magnetic field that is anchored in the accretion disk and is threading the black hole, goes as the black hole mass squared times a function of the black hole spin f of j. I use j to represent the dimensionless black hole spin following Blanford and others, such as Meyer. But you might be familiar with A star or A as the representation for the dimensionless black hole spin. I use the J. And the black hole spin function f of j over f max goes as capital F squared, where capital F is j divided by the square root of j divided by 1 minus the square root of 1 minus j squared. Now, in this equation, the maximum value of this f max is automatically 1 when j is 1. But in some numerical work, such as that in Tchaikovsky et al. 2010, a different function is written down for f of little j here, where it's not normalized to be 1 when j is 1. So I included this little f max in case this is going to be applied where f of j is not normalized to be 1 when j is 1. Now, to first order in j, it's the square root of f of j over f max, or capital F, that goes as j. So in the results I'll be showing you, we'll be looking at the square root of f of j over f max. All right. So now, in 2019, I wanted to take this theoretical equation and rewrite it in a form that was similar to the empirically determined form that I obtained between the beam power and the Eddington normalized beam power and the Eddington normalized bolometric disk luminosity. So to do that, I use this quantity called the Eddington magnetic field strength, which was introduced in the 80s. It's discussed in Martin Rees's 1984 review paper and several other papers by Rees and others. This is the Eddington magnetic field strength is defined so it has a pressure similar to that of a radiation field with the Eddington luminosity. And it scales as the black hole mass to the -1 power. B sub ed squared scales as mass to the -1 power. So we can take this theoretical equation and take 1 power of the mass over to the left-hand side to get Lj over L ed, and 1 power we write as B ed squared, and factor out B poloidal over B squared for the disk magnetic field strength, absorb that into G sub j, and write this as G sub j, a normalization factor, times the magnetic field strength of the disk in Eddington units squared times f of j over f max, okay? So what this does is it takes our theoretical equation describing a spin-powered outflow and writes it in dimensionless separable form, okay? So we see the outflow, Lj over L ed, and including G sub j, is described here. The accretion disk properties, B over B ed squared, are described by this term. And the black hole spin is described by f of j over f max. So it separates into 3 different parts. Now, B poloidal over B squared is absorbed into the coefficient G sub j. And for now, I'm taking that to be constant. However, it is possible that there is some variation in G sub j. All right. All right, so now let's compare the empirically determined relationship, Lj over L ed goes as L bol over L ed to the A, purely empirically determined, no models in that at all, and our theoretically predicted relationship for a spin-powered outflow written in dimensionless separable form. And now we can identify terms. Okay, so obviously here's the outflow, Lj over L ed, and we see we have a term here that L bol over L ed to the A that applies to the full accretion disk, not one particular component of the accretion disk, and B over B ed squared also applies to the full accretion disk. So we identify these terms. Now, I should say that in the original paper, the 2016 and 2019 papers, there are a few other ways to arrive at the same conclusion that do not rely on this identification. So this is a simple, easy way to find this result and understand this result, but there are other ways to arrive at the same conclusion. So we realize we can obtain the quantity B over B ed squared empirically, and then we can take B ed over to the right-hand side and solve for the magnetic field strength of the accretion disk by basically removing the mass dependence that's in the Eddington magnetic field strength. We can also now take this relationship and substitute it back into our theoretical equation, eliminating b over b ed squared and substituting in L bol over L ed to the A, and thus solving for the black hole spin, capital F squared, empirically, okay? Now, when we solve for capital F squared empirically, occasionally it is larger than 1. And so when we go to map capital F to J, our spin, we have to take values of F greater than 1 and map them to a spin of 1, because this does not allow values of J greater than 1, this term square root of 1 minus J squared. When this equation is used, this equation for F squared is used empirically to empirically determine the spin, a value of G sub J of 0.1 is used for all sources, and a value of G sub B of 1 is used for all sources. Of course, we always keep in mind that G sub J, might be different for different types of sources, and that is work that I'm working on now, but I'm not going to be reporting on that today. All right, so here are the empirical results for B over B ed in terms of L bol over L ed to the A over 2. And in terms of uncertainties, so here are the uncertainties of log of B over B ed for the different samples. So in order, it's the liners, the FR2s, the Merloni et al. Sample for 2003, and the galactic black holes. So I refer to the stellar mass black holes that are in our galaxy as galactic black holes. They have masses of around 10 solar masses. Now we notice that the B over B ed squared, which we will learn later on, is related to the dimensionless mass accretion rate. But for now, this is a function. It does vary by AGN type, and that was known in it already and is expected. Okay, that L bol over L ed varies by AGN type. C for galaxies, FR2 sources, etc. So that's easily visible here. Now we can remove the Eddington magnetic field strength by multiplying by it, and it turns out to be in units of 10 to the 4 Gauss, around 6 divided by the black hole mass in units of 10 to the 8 solar masses to the 1/2 power. So this is showing the magnetic field strength of the disk in units of 10 to the 4 Gauss. And interestingly, we go from this, which is what's obtained directly, empirically, and unwrap it to get the field strength. And we notice that these are all lining up at field strengths of about 10 to the 4 Gauss. And 4 sources in this sample that had independently determined magnetic field strength with independent methods that do not rely on the outflow, they're only looking at the disk, the values agree quite well in terms of the magnetic field strength. And similarly, for the galactic black holes, the stellar mass X-ray binaries, typical magnetic field strengths for the disks in those systems is about 10 to the 8 Gauss, which is what is recovered with this method. So that was very encouraging to go from this to this, and indicates that this method is reliable and it's on the right path. All right, now I thought it would be helpful to take a moment and look at some of the results for the spins for the whole samples. So here are the results for the spin function, capital F, for the 576 liners, the 97 FR2 sources, the 80 AGN in the Merloni et al. 2003 sample, and the 102 measurements of the 4 galactic black hole systems. So here are the values of capital F. Here, the first number here, this minus 0.04, is the mean value of all the sources, 576 sources. This is the dispersion of that sample, and the uncertainty per source is indicated by the number in brackets. So it's around 0.14 for per source in the Nisbet and Best sample, and it varies a little bit from sample to sample. So we see that for the Nisbet and Best liners and the 97 FR2 sources, they come in with very, very similar spin values, indicating a mean value close to 1, close to a spin of 1. And what happens is when we map from capital F to J, since anything that had a value of capital F greater than 1 got mapped to a spin of 1, that pulls down the overall mean value of spin for that sample. Interestingly, on our original figure of LJ over L Bol versus L Bol over L Ed, there's almost no overlap between where the liners fall and the FR2s fall on that diagram. Now for the 80 Merloni et al. Sources, AGN, and the galactic black holes, these are lower. So these are coming in with spins more like around 0.9 for the galactic black holes as a mean value, and around 0.8 for the Merloni et al. Sample, which has a very, very large dispersion. Now, down in the bottom part of this table, I'm comparing results obtained with this new method shown here and results obtained independently. So the galactic black hole system, GX339-4, for the, I used the Sakai et al. Paper where they had the simultaneous radio and X-ray luminosities. And there were 76 simultaneous values of those for this source. So I was able to get 76 independent measures, or measures, possibly not independent, but measures of the spin, the accretion disk, field strength in Eddington units, and the field strength in physical units. Now, I'll show you later on a diagram, almost none of these have values of capital F greater than 1. So there's no impact on going from capital F to J of mapping F to J for this source. The mean value came in at about minus 0.76, plus or minus 0.01 for capital F. That mapped to a spin of 0.92, plus or minus 0.06. And there is an independently determined spin for that using the X-ray reflection method, which relies on the shape and magnitude of the iron K alpha iron line. And those are reported as coming in at around 0.94 or 0.95, plus or minus 0.02 or so. So very, very nice agreement here between these independently determined spins. We will notice that the dispersion of the 76 measurements on capital F is around 0.06. Whereas the dispersion on the field strength in Eddington units or in physical units is 3 times larger, about 0.18. When we look at a diagram of these values, this is very striking. And what this indicates is that as the accretion disk changes, so over time, as this source is observed over the course of time, the properties of the accretion disk are changing, the properties of the outflow are changing, leading to these large dispersions over here. However, the properties of the spin have a factor of 3 smaller in dispersion, or a factor of 6 smaller. If we looked at m dot, this will turn out to be little m dot b over b hat squared. So the accretion disk properties are changing, but the spin that you determine with this method remains fixed as expected, because the time scale for the outflow to modify the spin of the black hole is very long compared to the outflow timescales here. In case anyone is interested, the 3 other black hole systems are shown here with the number of observations per source, and here are the spin values obtained for those other black hole systems. And in this paper, in the discussion section, I added another observation of A06200 from 1975 when it was observed in outburst. And it comes in with pretty much the exact same spin value, although the accretion rate and the magnetic field strength are very, very different. And we can compare results obtained for half a dozen AGN with those, so obtained with the X-ray K-alpha iron line method. I can compare those with the results obtained with the spin powered out method, the outflow method, and there's relatively good agreement for those sources that overlap. Now I see, I don't know how I'm doing on time. Looks like I'm already running out of time. So I'm gonna have to speed this up a little bit. All right, well, here are the results for capital F, which I plotted versus B over B ed squared. And here is an F of 1. So this would be the maximum possible spin. And we see there is a spillover to higher values, which is within the expected uncertainties for the sources studied here. Okay, so here's the uncertainty per source in this diagram. The X-ray binaries we see are pretty much all located down here with spins below a capital F of 1, and they also have a much smaller uncertainty per measurement. Now mapping this over to the spin J, everything with an at capital F greater than 1 gets mapped to a spin of 1. And so that leads to a large number of sources here. And then everything in this part of the diagram has a spin of 1 or less. We see the Merloniol sample extends to relatively small values of spin, about 0.4 or so. And that's because it's a very local sample and goes very deep into the luminosity function, whereas the liners go out to a redshift of 0.3 and the AGN go out to a redshift of 2, fairly evenly distributed in redshift. So looking at the histograms for the spin J, we can see the broad range of values for the Merloni et al. Sample, and the other sources tend to pile up at relatively high values of the spin. And I didn't include a lot of the redshift, showing these as a function of redshift, but I included this one just to give you an illustration that how the flux limited nature of the surveys used for the liners and the FR2 sources lead to a selection effect where you're missing the lower spin sources at higher redshift. Okay, so we can see that for the Nisbet and Best sample, which goes to a redshift about 0.3, and the FR2s, which go out to a redshift of 2. And the Merloni et al. Sample is all quite local, so it does not suffer from that effect. For those of you interested in stellar mass X-ray binaries, this is showing the spin function log of capital F versus log of B over B ed squared, which is also will turn out to be little m dot, the dimensionless mass accretion rate. We see this cluster of points over here where each observation is shown separately. The measurements for GX339-4 are shown as open circles. For the 20 measurements of V404 sig A are shown as crosses. 5 measurements of XTEJ1118 are shown as the triangles. 1 measurement of A06200 is shown here. As I mentioned in the discussion of the 2019 paper, I include the value for the 1975 X-ray FLIR. That moves that source over to here. Interestingly, the spin comes in almost exactly the same with that other data, but the field strength is much, much larger and puts the source over here in this cluster of other cluster of sources. So it almost looks like for the stellar mass black hole systems, there's sort of a certain range of parameters where they have the spin powered outflow, and then these points might be catching these as they're entering or exiting this particular phase. All right, now independent of the results I've shown you, we can think about the mass accretion rates and whether or not the sources could be used to study the mass accretion rates and efficiency factors of these systems. So the beam power can be written as the mass accretion rate in physical units times the black hole spin function, capital F, squared. All right, so since it's a spin-powered outflow, we need to have the spin term, capital F squared, and then from a dimensional argument, we're going to have this go as the first power of the mass accretion rate. Now, I define the dimensionless mass accretion rate in terms of the physical mass accretion rate in this way, capital DMDT divided by the Eddington luminosity, without including the efficiency factor of the radiant luminosity of the disk in the denominator. So sometimes when people study the mass accretion rate and convert from the physical mass accretion rate to the dimensionless mass accretion rate, the efficiency factor of the bolometric luminosity of the accretion disk, which is defined with this equation here, is absorbed into the denominator of this relationship. I had already found in my 2016 paper that for these sources, for the FR2 sources, this bolometric luminosity cannot be left as a constant. It must be included as a variable for the sources that are being discussed here. So for that reason, I leave it as a variable to be determined and discussed. So you might keep in mind that in some papers, the dimensionless mass accretion rate is defined in the same way that I'm defining it here. And in other papers, it's defined, including this bolometric efficiency factor in the denominator. In any case, using this definition and this relationship between the beam power and the mass accretion rate, it's easy to show that we can write LJ over LED is our normalization factor G sub J times dMdt, the dimensionless mass accretion rate, times F squared. So once again, we identify terms here, and we can write that the dimensionless mass accretion rate is B over B ed squared, which we already found was L bol over L ed to the A. Now we remove the definition we put in and solve empirically for the mass accretion rate in physical units, capital dMdt. And this has been obtained independently by other groups for a few sources that overlap with the sources I'm studying here. And in those cases, there is reasonable agreement between the values obtained with this method and those values obtained independently. So once we obtain the physical mass accretion rate empirically using this equation, we can use it to empirically determine the bolometric efficiency factor of the disk, okay? So using this standard definition between the bolometric luminosity of the disk, the efficiency factor, and the mass accretion rate, we simply put that in over here and find that the bolometric efficiency factor of the disk for the types of sources studied here is L bol over L ed to the 1 minus A. Typical values of A of around 0.45 would give this L bol, epsilon bol is going like dMdt to about the 1.2 power. Now, so far, no particular accretion disk model has been assumed or adopted, okay? So we can go back and look at what types of accretion disk models are consistent with this, which is not, I'm not going to be discussing that today. Now, there's another efficiency factor that it's really interesting to look at, and that is what I call the spin to disk efficiency factor, defined in my 2019 paper, actually defined in my 2021 paper, and it goes as F squared over m dot, and it's basically providing a measure of how much does the beam power depend on the spin, F squared, the spin function, and the dimensionless mass accretion rate. So this ratio, F squared over m dot, is a measure of the relative importance of these two terms in determining the dimensionless beam power. And it turns out that this goes approximately as LJ over L Bol. In other words, your intuitive sense that the ratio of the beam power to the disk luminosity should reflect the relative importance of spin relative to accretion is in fact borne out when this efficiency factor, the spin to disk efficiency factor, is written in terms of empirically determined quantities. I feel like I'm running out of time. It's 2:22. I'll just go over this very quickly and then probably skip to the end. So now, solving for those bolometric efficiency factors, there's a very, very interesting result. And for those of you interested in uncertainties, those are included up here for these sources. And what is found is that the Merloni et al. Sample shown in red here separates into two parts. And one part overlaps with the FR2 sources and the galactic black holes. And these are radiatively efficient accretion disks. They have high values of L Bol over L Ed. And another part of the Merloni et al. Sample lines up with the liners, and these are radiatively inefficient disks. So it's rather interesting that the empirically determined bolometric efficiency factor splits the Merloni et al. Sample into two subgroups, one of which overlaps with the radiatively efficient disks and one overlaps with the radiatively inefficient disks. I did write this as a function of redshift here, just so you could see the cutoff at the bolometric, when the bolometric luminosity of the disk matches the Eddington luminosity, okay? So this is just one way to see the very strong cutoff of the bolometric luminosities determined here, where there are very, very few sources that would be have a disk luminosity greater than the bolometric luminosity of the disk. You can also see the strong selection effects coming in here, for example, on the Nisbet and Best sample, where you're missing the bright sources at higher redshift. Very quickly, we can compare the efficiency factors and mass accretion rates obtained with this method with those obtained independently there were 6 AGN studied by Raimundo et al. In 2012 that overlap with the sources included in the samples I studied. And in Raimundo et al., they calculated the bolometric efficiency factor and the mass accretion rate. And they got the efficiency factor in using 2 different methods for some sources. Now in Raimundo et al., they're looking at a specific accretion disk model, and they do not account for the outflow at all. In other words, these 2 methods are completely independent. The outflow method that I'm using and have developed relies on a comparison of the outflow properties with the a spin-powered outflow model. I mean, the basic equation that describes a spin-powered outflow and identifying terms. So it's really interesting that the results for both the mass accretion rates in physical units and the efficiency factors agree reasonably. So I'm going to speed up a little bit. I'm starting to run out of time. So here are the efficiency factors I obtain. Here are the efficiency factors Raimundo et al. Obtained. Here are the ratios, and they agree to factors of a few, which is about what I would expect given the uncertainties in the model that Raimundo et al. Is using and the uncertainties, empirically determined uncertainties for the bolometric efficiency factors. There's one source that's off by about a factor of 10 or so for the efficiency factor. Now, because the outflow method relies on a comparison of the disk properties and the outflow properties, it's important to have simultaneous or contemporaneous radio and X-ray measurements. For the AGN I've studied so far, those measurements are not simultaneous or contemporaneous. So one possible explanation for this offset is that, that the data going into my calculations for the AGN so far are not simultaneous or contemporaneous. In comparing the mass accretion rates in physical units, there's relatively good agreement. Here's the ratio. There are two sources that are off by about a factor of 10. And we did get some observing time, myself and some collaborators, where we are going to have simultaneous radio and X-ray data for a substantial number of local sources with mass accretion rates determined using methods like Raimondo et al. And Zhang et al. And spins obtained with the X-ray reflection method. So that will be that will allow us to test what the impact of having non-simultaneous and non-contemporaneous radio and X-ray measurements are. In 2019, Zhang et al. Published dimensionless mass accretion rates, and I can compare them with the mass accretion rates obtained with the outflow method for 8 sources. And here are the ratios of the values, okay? So they come in relatively consistent to factors of 2 or 3, which is about what you would expect given the uncertainties of the model used by Zhang et al. And the empirical uncertainties that go into their model, the empirical uncertainties that go into the model that I developed, the outflow model, and also the fact that these are non-simultaneous measurements, so that could impact the values that I am obtaining. But I think this agreement is quite encouraging and quite reasonable given the uncertainties. All right, well, for those of you interested in the dimensionless mass accretion rates, they're shown here. I'll speed this up a little bit. Here are the accretion rates in physical units. And interestingly, for the stellar mass black hole X-ray binaries, detailed mass transfer models, mass transfer and accretion disk models, actually come in with physical values of mass accretion rates that are very, very similar to the ones I obtained here and overlap with the values I obtain. Again, the ones obtained and published independently have no input from the outflow. They're only looking at the properties of the accretion disk. So that's very encouraging agreement. We see in terms of capital M dot, the mass accretion rate in physical units, the Merloni et al. Sample does not split into 2 samples and looks like a relatively by eye continuous range of mass accretion rates in physical units. I think I'll skip the spin to disk efficiency factor. I see I'm running out of time. So I'll just go to my primary conclusions. The primary results are that there are 3 empirical indications that the outflows are spin powered. The first are the very, very large beam powers compared to the disk luminosity. The second is that the field strengths obtained in that model agree with those obtained independently in the context of specific accretion disk models that do not include the properties of the outflow. Same occurs for the mass accretion rates and efficiency factors. The ones I obtain agree with those obtained independently in the context of specific models that don't consider the outflow. The black hole spin is unrelated to source type. So the type of black hole, the black hole spin values and ranges are very similar for all of the sources studied, the galactic black holes, the liners, the local AGN by Merloni et al. That includes Seyfert galaxies and liners, and the classical double sources. And in fact, that had already been obtained in 2016 for the classical double sources on their own. You could see right away there was no relationship between AGN type and black hole spin. The spins obtained range from about 0.6 to 1, with the possibility that the preponderance of high values, especially going to high redshift, may be due to selection effects. And finally, the method and results are all empirically based. They do not, it's independent of any specific accretion disk model and independent of a specific jet model that relates the radio emission to the outflow beam power. So we can now take these results and ask what types of accretion disk models and jet formation models in terms of the size of the jet at its base, how it's related to the magnetic field structure of the jet, et cetera. We can see how these, which models are consistent with the results obtained here. Thanks. I'll stop there. Thanks.
All right. So let's thank Ruth for an amazing talk, and we have some time for questions. And yes, Salvatore.
Thank you, Ruth. I am Salvo. So this was a lot to unpack, and I work on gravitational waves, which is pretty far from here. But actually, that's what my question is going to be about. In LIGO land, where mostly find spins very, very small, like, or in most cases consistent with 0. So I guess starting from your conclusion slide, I'm trying to reconcile the two things together. And so first of all, I wanted to understand your perspective on whether it's possible that the ice spins that X-ray people have been finding may be due to selection effects, are certainly due to selection effect. Or if not, how do you personally view right now the dichotomy between all the EM-based methods finding preferential large spins and the only method which does not use photons finding preferentially small spins?
Right. Just trying to move some things around here. That's a great question. One possible explanation are selection effects. AGN and black holes that have accretion disks but small spin would not produce a collimated outflow. The source, all of the sources that I'm studying have a collimated outflow. It's not possible to apply this method to a source that does not have a collimated outflow. So I think there's a strong selection effect there. Another possibility that I'll sort of throw out there is, well, that's another topic. I think I won't mention that. But anyway, the black holes that LIGO is studying also don't have accretion disks, as far as I know. You know, they're sort of bare black holes. So that would be another possible explanation. And in addition, the LIGO results study one particular, you don't really, I mean, I understand you can study the black hole spin, but it's a combination of spins and the orbital plane, and it's projected, you know, so you're sort of studying one component of the black hole spin of the system. So in any case, it doesn't worry me too much. I chalk it up to selection effects. And it could be that as LIGO measures more and more sources, there will turn out to be a component that have higher spins. I mean, I guess I will throw out and mention that I'm sure you all know that the spin energy contributes to the black hole mass. And the black hole masses measured by LIGO are total dynamical masses. So up to 30% of the mass, of the dynamical mass, can be contributed by the black hole spin. Or another way to look at it is if you write the total black hole mass in terms of the irreducible mass, you can increase the black hole mass by 40% by including the black hole spin. So I often wonder if the spin is possibly, for the LIGO sources, yielding the population of very high masses that are sort of outside the range of masses that people predict. So the spin could be showing up in the black hole mass being large. But I do understand that when you look at the this chi-effective, I think it's called, spin function, which is has to do with the relative orientation of the and how those are related to the orbital plane of the black hole. So it's complicated. It's a complicated equation, but don't lose sleep over it, because if it's not going to come in as the mass explanation, I think it could easily be a selection effect on my end, on the end of the AGN and the black holes I'm studying. Eventually, we'll understand this well enough to be able to say what fraction of stellar mass black holes that are parts of X-ray binaries have high spin. But we're not near that right now.
Thank you.
Alex.
Yes, thank you for this introduction to the outflow method. I wasn't familiar with it. So I had heard of the X-ray reflection method, and for stellar-sized black holes, the continuum fitting method. So you showed us one cross-check with the X-ray reflection method. Are there more than one? And is your method applicable to stellar-sized black holes? And if so, does it agree with the continuum fitting method?
I started continuum fitting method now, so I haven't done that yet. Can you see the table shown here? Okay, great. This shows all of the sources that have an X-ray reflection spin that overlap with the sources I studied. Now, for the AGN, we recently were awarded about 30 AGN with known determinations. And we will, for those 30 sources, be able to compare with simultaneous X-ray and radio data the spins obtained with this method. I have to look more at the stellar mass black holes. To tell you the truth, that's not my, that's not something I've worked on in the past, so I have to read up on that a bit. But I know that I think for A06200, the continuing fitting method, I believe, gave a smaller value for the spin. However, when I looked at the second data point for that from the 1975 X-ray flare, I came in with values where the accretion rate went from being very, very low, obtained here, to being very, very high, obtained in 1975, but the spin stayed exactly the same at the high value. So it may or may not be the case. I have to look into that more. I'm not really prepared to make a statement about the continuum method and when it does and does not agree with the X-ray reflection method or the outflow method. So TBD on that.
Great, that would be very exciting, because whenever you have only one method, maybe it doesn't work. But if you have two and they agree, that would be amazing to get.
Right. Well, Belinda Wilkes and her collaborators and students and postdocs are working on X-ray continuum method, and they recently published a paper using that for 3C quasars that overlap with a lot of the quasars I have. And there, the agreement in the spin values is excellent. We're coming in with exactly the same spin values. Well, very, very similar. Definitely within uncertainties. And so I'm going to be starting to look at that. And that will probably spill over into the continuum method applied to stellar mass black hole systems.
Thank you.
Sure.
All right, so I don't see more questions. So let's thank our speaker, Professor Daly, again for an amazing talk. And just a quick reminder that at 5 p.m. today, we'll have a special panel during which a number of local EHT members will be presenting on the recent M87 polarization results. So tune in if you're interested. And other than that, we'll see you next week. Bye-bye.
Bye. Thanks, and thanks for having me. It's a pleasure to
Thank
be
you.
here.
Thank you for the talk.
coming.
Thank you.
Bye.